Starting 2.9, talking about linear approximations and differentials. So the idea for linear approximations is just as we calculate a function's value, so after we have some x and we're trying to find out what the y might be, there might be situations where it's easily calculate. I can plug in a number and get an answer out, right? I can find my y pretty easy. But there might be some functions that maybe the maybe the points right next to it might be really difficult or impossible to find. So then we can go ahead and we might be able to find this value right here, but maybe this value next to it is really, really impossible to find or something like that. I mean, this is an easy graph, of course, but maybe there's some type of function that it might be difficult. So we can go ahead and calculate that derivative, right, and write the equation for a tangent line going through that. And then we can use this graph of this linear equation, right, y equals mx plus b, which m is just our derivative at that point right here. And so we can go ahead and calculate, say, this value right here by approximating the value right here on this tangent line. So as long as we can get really, really close, we can plug in our x into this linear equation to find a really close value to this one right here. So that's the kind of idea for linear approximation, is to use that tangent line in order to estimate our values. So we know that we're writing that equation of the linear right there, y equals mx plus b, where this m is our derivative, right? So that's like f prime of a, right? That's our slope if I plug in some x value, a, and get my derivative. And I plug that x value into that equation. So that's my m, and then I just need to solve. I could put it in point slope form. Right, and this is just f prime of a. That's what my slope is. And then the point that I'm using is this point right here. Well, that was plugging in my a and getting my y value, which is f of a. So just f of a. So my y value is f of a, right? Plugging it into the original equation and finding it. And then we have our slope, which is plugging in a into our derivative. And then our x value is a. So let me go ahead and solve this for y. Y equals, add f of a to both sides. Oops, plus f prime of a. So this, then go ahead and switch f of x to, or y for f of x. So we have this, and this is just our approximation of the original function. So when I plug in my values into this tangent line, it's approximating values for my function. So it's approximating, so that's why you use this symbol, because we're just using it as an estimate. So we're using this line, this green line, to approximate my values of the red curve, right? So approximate. So this is called the linear approximation or the tangent line approximation. So I'm just approximating what my curve might be off of that tangent line. So this is called the linear approximation. So we can use that to approximate our value of our curve using that tangent line. And then if the book asks for the linearization, so the linearization of a value of some given a, then we would use this one. So the linearization is just changing it basically to a capital L. So linearization is using the same equation. We can just say equals. So that's approximation is this one. Linearization is with the capital L, but the same exact equation with an equal sign. F prime of a times x minus a. So the equation of the tangent line is y equals the linear approximation is f of x is approximately the same equation. And then we have the linearization, which is L of x equals that equation. So look at when the book is asking you to do different things, you're really using the same equation. It's just this is approximation, this is linearization, and the tangent line is just y equals. All right, so this one is looking for the linearization of the function. So that means I need to write my equation, linearization of the function of a plus f prime of a, oops, prime of a, not double prime, just one prime. X minus a, or yeah, x minus a, which my a is 1. Okay, so I have to find f prime of a. So that means I'm taking the square root of x plus 3, rewriting that as a half power, and now I do the chain rule. So 1/2 x plus 3 is the negative 1/2. And now I could go ahead and rewrite that. Half power is a square root, and a negative half power is just bringing it to the denominator. Okay, and now I can plug in my a, which is 1, or my x. So plugging in 1, that's 4. Square root 4 is 2. So we get 2 times 2 on bottom, so we get 1/4. So my f prime of my a, which is 1, equals 1/4. So that's 1/4 times x minus a, which is 1, plus f of 1, so that'd be plugging in 1, which was square root of 4, which is 2. So there's my linearization. So that's linearization of my function. And I could simplify that. 1/4 x minus 1/4. That'd be the same as 8/4 minus 1 would be 7/4 x plus 7/4. So that's a linearization of my function, simplified. So what this means is this, when I plug in an x into here, it's going to be really, really close, so approximately close to the same thing as plugging in square root of x plus 3. So why you do linear approximations, because this problem really might be really impossible to do. This one's not, of course, but it might be, so it's better to plug it into this one to approximate that value. So that's why you use it. Now the ones we're going to be dealing with is mostly can be done. That's why, because they're derivatives, they're easy to find. But so if you do it in a different problem, it might be impossible to just plug in x and solve for it without a computer program or something online or something like that. And this is only true when you're plugging in values for x that are close to 1, so that are really close to 1. So plugging in 1 always works, but maybe like 1, you want to find 1.2. So it'd be easier to plug in 1.2 into here than into here. So then let's go ahead and approximate these values. So they gave us these values, square root of 3.98. So let's approximate it using this formula. 1/4 times x and plus 7/4. So I got to plug in my x here. My x, this is x plus 3, so my x would be just the 0.98, because 0.98 plus 3 is 3.98. So my x is 0.98. So this is 0.98, or approximately 0.98/4 plus 7/4. So which would be 7.98/4. And now I could do that on the calculator, maybe easier than I can do that, or at least by hand. So that is 1.995. And then if I do the square root on my calculator of 3.98, I get a, pretty close to the same thing, 99499, and then it kind of keeps on going. So it's pretty close. It's approximately close. Okay, and then you can go ahead and you can do the other one. You can try the other one yourself. So you can do 0.05. So my x would be 1.05. So my x would be 1.05 that I plug in here. So that answer, if your x is 1.05, is 2.0125. Sorry, 2.0125. And the actual value is 2.0124617. It keeps on going. So pretty close. All right, so now we're going to talk about differentials. Um, so when we find the derivative f prime of x, we can use that notation, or we can do dy over dx. It means we take the derivative of y with respect to x. And before we kind of just left this as just a whole, and but now we're going to treat it as their individual numerator and denominator. So when we have differentials, what we're basically doing is just solving for dy. So we can turn this into a fraction, so I can just multiply both sides by dx here. So then when I ask you to solve for the differential, basically what you're doing is solving for dy. So that just means that you take the derivative of your function and times that by dx, and you just leave it in terms of dx. So that's what basically differentials is. So here's an example. So we want to compare the values of the change in y, right? That's the difference in my y, so that'd be me finding my y, so 2 and 2.5. So I'd plug in 2, right? And then I'd plug in, take the difference of that, subtract, plugging in my 2.5. I probably would put in 2.5 first because it's bigger. So it's probably going to get a bigger y. So then I don't get a negative here, but that's okay. 2.5, 2.5 plus 1. I need to add a 1 here. So you plug in those numbers. And we plug in 2, we get 9. And then we plug in 2.5 in for our x's, and we get 9.717625. So I'd subtract these, and I get 0.717625. I probably should have switched around because I get a negative here. Okay, so we're going to compare, that's the change in y. And so now we're going to compare that to dy. So dy is just taking the derivative of this function. So taking the derivative, f of x equals x cubed plus x squared minus 2x plus 1. So that'd be 3x squared plus 2x minus 2. So that's the derivative, right? So then all I have to do is just times it by dx. Because remember, the derivative is just dy over dx. So if I'm solving for dy, I just multiply both sides by dx. All right. That's f of x. Okay, so I just multiplied by dx there. So dy is equal to 3x squared plus 2x minus 2 times by dx. All right, like that. And so now I just go ahead and plug in. Now I can plug in when this time my dx would be 0.05 and my x would be 2. Because the dx is just like the change in x. So my change in x is 0.05, and my x is 2. So we're comparing these, and times by the change in x, or dx, is my differential. And so solving that, it just becomes 0.07. And so we can compare the two. 0.07, this is not 0.07, 0.7. So we can see it's pretty close. 0.7 is dy, and the change in y was 0.71. So pretty close. So it's easier to, instead of just finding the change in y, we can find dy, and it's a lot easier to do. All right. All right, so we're dealing with estimating errors that occur because of the approximation measurements. So we have a sphere with the radius of 21 centimeters, and we want to find the possible error between 0.05 centimeters. And so we want to find the maximum amount of errors. So anytime we're finding maximum or minimum, that means we're finding the derivative. So, and we want to find the possible error in measurement if it's 0.05 centimeters. So we want to find the max error with the radius for the volume. So we're going to find relative error and then our percentage error. So first we need volume of sphere, and volume for a sphere is 4/3 pi r cubed. So then we're going to take the derivative of that because we're looking for the max. So that means, right, a max here with the tangent line, slope would be 0. So you're looking for the derivative. So dv. So I'm going to go times this. Put the 3 out in front, cancels with the dividing by 3, so we get 4 pi r squared. And then since it's just dv, because normally it's dv over, this would be dr, because that's in terms of r. So we multiply both sides by dr. So we get dv by itself. And so now we can go ahead and plug in our change in r. Our change in r would be the change in our error, which is 0.05. And then we can plug in our radius. Our radius was 21. And so then we can find dv, and it's approximately 277 cubic centimeters. So that would be our max amount of air that our volume can have. So there's that. And then relative error. Since this looks a little large, we can find our relative error. So that would be our max amount of air, which was 4 pi r squared dr. Divide that by our total volume. It's 4 pi thirds r cubed. So that's going to cancel. Right, the 4's are going to cancel. Pi's are going to cancel. R square is going to cancel, so we're just left with r on bottom and a dr on top. So 3 goes to the top with dr over r. So there is our relative error, and it's about 3 times. So our relative error is about 3 times the size of the radius. So 3 times. So this is what it would sound like. The volume, the relative error in the volume is 3 times the relative error in the radius. So the relative error in the radius is taking our dr times in by 3, which is 0.05, over our radius, which is 21. So that's approximately 0.0024. So that number might seem a little better. And then our percentage error would just be changing that to percent, so 0.24%. All right, that's it for 2.9.